Our last speaker is Abanoub Ghobrial from the Trustworthy Systems Laboratory at the University of Bristol. He is a research associate at the Computer Science Department, working on cutting-edge technology for simulation-based autonomous vehicle verification in the context of the Innovate UK projects, Capri and RoboPilot.
Good afternoon, everyone. So, yeah, okay. One of the hardest challenges engineers are facing nowadays is the verification and validation of autonomous vehicles. I've already heard a couple of talks so far today about this. But yeah, one question that we get to hear very often is how safe autonomous vehicles meant to be? And there's all sorts of debates and articles on how safe that they ought to be and all of that. But one thing that we all agree on is that we definitely need simulations in order to be able to verify autonomous vehicles and validate them. So we're at the Trustworthy Systems Lab in collaboration with the Bristol Robotics Lab at UE. We're looking at intelligent testing of AVs and simulation. And I'm Abanoub, as I've already been said. Yeah, I'll be walking you through this. So we're working on two projects, RoboPilot and Capri, and they're both autonomous driving projects. On the left here, you can see the autonomous vehicle, the RoboPilot autonomous vehicle, and this is directed more towards goods delivery, while the Capri project is directed more towards urban mobility. And I've got a little Venn diagram here showing all of the partners. You can see they're all quite big names. We sit in the middle here, taking a leading role in the verification in developing verification and validating techniques which can be used then by the companies to be able to verify and validate their software. So going into the challenge of AVs verification and validation, and by the way, when I say AVs, I mean autonomous vehicles. So how do we verify autonomous vehicles? So there's a number of things that we need to look at. So far we said that simulations are definitely has many benefits over real world testing, and these are, you could safely cause dangerous scenarios without killing anyone or harming anything. You've got the benefit of being able to do parallel test runs, which definitely saves a lot of time. You've got full control over the environment state, and it's more cost effective. But then in terms of the verification goals, or what you need, so the things that we need to look at in terms of to be able to verify the vehicles, these would include the rules of the highway code, and then you've got social conventions. And social conventions in particular is a very, very challenging bit right now in the industry. Things like how would an AV interpret an autonomous vehicle, another vehicle flashing their lights at them, or someone waving at them. And then we've got coverage as well. But then how can we do this efficiently? And how can we efficiently target verification goals? Well, the answer to that is just another question. And that's what we're trying to answer in our research. And that's, can we use multi-agent systems technology to generate effective tests automatically? Or are there any other intelligent test generation techniques? So just to summarize this slide up, our goal is to develop an intelligent virtual testing environment that can be used then by companies to carry on the process of verifying their system, and then assess it, whether it fails or passes. So moving on to our test bench now. So we can break the test bench into four main big chunks here, as I've highlighted in these dashed box. You've got the one on the top left here, where you specify the test. This feeds it into the script that communicates to the simulator, and this script would generate the test and control the agents or the actors. And then at the same time, you'd have the autonomous vehicle control binaries, and this would be developed by the company, or be a property of the company. and this would communicate directly at the same time to the simulator. And at the end here, you've got the assertion checking loop, which just loops the whole time to check if the AV has breached any laws or has done any assertions, basically. So moving on into our simulation environment, got a little video here. So we're using Unreal Engine 4 as our simulator, and you can see here that the Rover Pilot vehicle roaming in our virtual environment. You can see it's pretty much photorealistic, so which is very beneficial because you can, I mean, the AV could obviously, you could run the real algorithms on there. Obviously, it could also be used for teaching the machine learning or running machine learning for the AV. So we can break our environment into three main blocks here. You've got the static entities, so things like roads, layout, bus stops, signs, bins, etc. And then you've got the dynamic agents, so things like cars, cyclists, pedestrians. And then we've got the environment conditions, which is lighting and weather. And we've got here 3 pictures showing the different actors and agents and the different environment conditions as well. So one thing that you ought to, or we ought to think about when we're talking about verification is how deterministic our simulator is. And just to recap, when I say deterministic system, it's a system that for the same experiment and given the same initial conditions, it would give you the same exact output. Just an example here, you've got a vehicle traveling at constant velocity, and you've got a vehicle that's traveling at constant velocity, and a pedestrian that wants to cross to the other side. But then, if you repeat this experiment, would it take the same exact path every single time, or would there be any variance? And if there is, how big would that be? How could it be minimized? And that's one of the things that we're trying to look at here, is that obviously, if there's any determinism, if there's any non-determinism, how big is it, and how could it be minimized? Obviously, we definitely need this, because otherwise, in verification, if experiments are not repeatable, then you won't be able to debug. And this sort of things is not guaranteed. I mean, game engines are not guaranteed the determinism is not guaranteed, which Unreal Engine 4 is a gaming engine. So moving to test generation, I'll be presenting three different test generation methods here. So starting with the first one, which is the natural active behavior. This looks great. The video is great, but this won't particularly target for rare events very often. I mean, on the other hand, it'd be very useful to look at traffic flow problems or congestion problems, but not for verification purposes. Our second method is the multi-agent system method, which is we're planning on using multi-agent systems technology to orchestrate challenging scenarios. This would definitely increase the efficiency of generating scenarios. Now, for example, here, if you want to test for collision avoidance, you'd have a number of pedestrians jumping out of the road to move from waypoint 0 to waypoint 1 in front of the vehicle, and see how the vehicle would respond. And obviously, as the AV would change its behavior, the multi-agent system loop would change to trick the AV. And our third, and perhaps most interesting, is the test generation game. So with this here, we've got. Have you ever thought of trying to? You want to test an AV, but you don't have the setup. You want to see what one AV would do in a particular scenario, but without a proper setup, even for a person in the same research field, they won't be able to do that. So here, this is just showing a little game that you could forge experiments together and make it run and see what happens. this would inherently lead to crowdsource test cases. So getting loads of people to play the game, generate different scenarios, try to trick the AV to do something to basically break the law. And if you can, then you get points. And I've got a little example here. This is a pedestrian walking their dog, and then the dog suddenly runs out into the road, and then you get a point up there. Another benefit of this method is that it would definitely increase the public confidence in AVs, because yeah, imagine I'm a person who's not on this research field, and I would like to assess what my AV would like to do, and then, as I already said, you won't be able to do that without a proper setup. So you just go here and you can simply just log on, forward your experiments, and see what happens. So moving on now to our assertion checking loop. This is pretty much straightforward. We're using a geospatial database, which is called Postgres. Sorry, Postgres. And this basically just logs the position of the AV, other actors, at the same rate of the simulation. For example, we've got a simple scene here, and you could easily query for off-road status or collision with buildings, distance between agents, traffic lights, stop lines, pedestrians, etc. And obviously, the benefit of using a geospatial database over is it's a lot easier to do it with geospatial database rather than doing pixel-to-pixel comparison. So just to sum up, our TSL research on autonomous vehicles verification and validation is focused on agents controlling the environment and the virtual environment, intelligent test generation, efficient techniques for assertion checking, and evaluation in the context of Ghobrial and robotic products. And these are all still ongoing projects, and we're still developing it further. So if you'd like to know more or get enrolled, just don't hesitate to contact the head of our lab, Kirsten Eder, or myself, or both. And I think that's it. Thank you, everyone.
Thank you. Thank you. Hello. Hi. Any questions? Okay. Come on, Paddy.
So I thought about your testing, and you were thinking of crowdsourcing, but you know, we've got so many cameras on our motorways and roads.
Yeah.
I was wondering if there's ideas to actually take that data and the accidents that the cameras will be witness to, and actually add those to, you know, see how the AVs would work in those situations. Yeah,
but one thing that one of the things that I didn't mention that we do, we've got our love for a partner looking at accidentology. So the accidents that happen with us as natural human drivers, basically, is not necessarily the same accident that would happen with an AV. So they've got different behavior, and this on the motorway or on cameras, no one's actually trying to trick vehicles into doing accidents. Yeah.
No, but you've got the situation, and you know, maybe we don't have a lot of AVs, but you know, you could put in one AV for one of the cars in the accident and see, or one of the cars going by, for example, and see what would happen.
Yeah, but then, yeah, you could use this as well. But what I'm saying is that you won't get as much. Basically, people would be more evil in this game, trying to trick the AV, rather than what happens naturally in what you were saying you'd get in camera. If you see what I mean? You would get tests. This is. One of our partners is doing that anyways, but it won't. What I'm saying is that it won't generate as much tricky scenarios as the game would do, if that makes sense.
I get it, but
yeah.
You know, I think of it as it's the minimum that you could do. That you'd have to work on, you know, the present accidents that are out there.
The minimum won't get us to being able to verify vehicles, autonomous vehicles. You need, basically, the government won't let you use them with a bare minimum.
Maybe take it offline, Penny. Okay. I think there's no questions online, so if there's no more questions, you wouldn't. There is one, sorry.
We could have a chat about it afterwards.
Yes, hello, I'm Ben Bradshaw from ZF. Just a quick question on how much you trust your validation model, how much are you sure it represents reality?
That's a good question. I'm not sure because we're still developing this, as in we're not in a state right now to assess how good it is. We're still in the development phase, so I think that's a bit that would come later on in the project.
So I'm on the same project, so I can probably answer as well. So what some of the models are representing physical trials. So the results we get from the simulation, we then check on the physical trials as well. So I guess it's a sort of digital twin type question, is it? What we're talking about. Yeah, it's a lot of the work does get validated in the physical trial as well. So, but it's a real problem, yeah. And the digital twin problem is a very real problem. So, yeah, I didn't know that you looked.
I thought you were stopping. Well, sort of carrying on with the digital twin, because you showed the picture was an arrival van, was it? The video, the original video. So
yeah, that one.
That's an arrival van. So are you going down? I mean, if there's I don't know if it's a stupid question, but are you actually validating? So if it was an issue with the brakes, are you validating?
Well, right now,
no.
The
brakes?
No.
Or is it just
currently? No, that's just roaming randomly.
That's just an avatar then, rather than anything else.
Basically, yeah.
So you can't actually, it's not going down to the homological, homologation.
I don't know what that means. I don't know what that word is.
I can't even pronounce it.
But it's the real control software.
I mean,
so you're testing control software rather than going. No, it's not going down to the actual actuators and the sensors, but it's mimicking.
It's only testing the software.
The control software.
And that vehicle is what Arrival develops. So whatever they want to test would be in that vehicle. Basically, it depends on how the level of how realistic they model their sensors and their actuators as well. So I guess it could be tested, but it's just how realistic they model things. Yeah. I mean, this would be another potential thing to add, I guess. Yeah.
Okay, I think that brings us to the end of the talk, so thank you very much.
Thanks.